Good morning and welcome to our first in-person class this semester. Before we actually get started with the lecture, I do want to, since it's so early in the semester, in fact our first in-person meeting, give a few announcements and remind you of how things are working this semester. First of all, in class you must follow all UA masking and social distancing rules. This lecture will be pushed onto your computer screen, so you need to log in as soon as you're seated, and that's really all you need to do, and you'll be able to see this lecture on your screen. On the other hand, I'm also planning to project it up front, so you should be able, assuming you're sitting in the view of it, be able to watch the video on the projection screen up front as well. Remember, this is a hybrid class, but class is never mandatory. You can watch the lecture, do the WebAssign assignment in advance, and then decide based on your performance and understanding whether or not you will benefit from coming to class. You will not be penalized for not coming, but if you need to be here, please be here. You have a lot of responsibility, so think about these things very carefully. Just a reminder, in this hybrid class, Tuesdays are our in-person classes. It's just going to be a lecture, not question and answer. That's the Thursday. Thursday is a Zoom-in virtual class, and it's just for student questions, and that implies that you will have already watched the lecture for that day in advance of Zooming in, and then you can ask questions based on the things you had trouble with. And just like for the Tuesday class, how well you understand the video lecture and how you do on the WebAssign assignment should be what you use to decide whether you need to Zoom that day or not. And be really smart and think through these choices you make. Remember my virtual office hours. They're posted in Blackboard, but every Tuesday and Wednesday from 1:30 to 2:30 you can Zoom in using the link in Blackboard and visit me during my virtual office hours. The MTLC has additional hours, and again you can get there through Blackboard, and the Capstone Center for Student Success also has tutoring available, and if you go to their website there's information about that in our orientation, PowerPoint, and video. Please feel free to use all these resources. They're there for your benefit, so use them. Please don't hesitate to email me if you have questions or concerns. There's no reason to sit there being confused about something when you could just shoot me a quick email and I probably could get you back on track. And remember, procrastination is your mortal enemy. That's the worst thing about a class like this where you have so much responsibility for being a self-starter and staying on track. And if you take my advice, even staying at least a little bit ahead, procrastination is your mortal enemy. Now to the actual lecture. Today we'll begin our study of Chapter 2 by talking about the basic properties of sets. Georg Cantor, a German mathematician who was actually born in St. Petersburg, Russia in 1845, is considered to be the father of set theory. In the beginning, many of his ideas were highly controversial, and he experienced strong resistance to his ideas from fellow mathematicians. Ultimately, his ideas prevailed, though, and in the process, he created the field called set theory. One of the ideas that Cantor had to deal with was the concept of infinity. Going back to the idea of a set, any group or collection of objects is called a set. The objects that belong to the set are its elements or members. For example, the set consisting of the 4 seasons has spring, summer, fall, and winter as its elements. There are 2 common methods for writing sets. First method is just describing the set in words. The second method is listing the elements of the set inside a pair of braces and using commas to separate the elements, and this is called the roster method. There's a third method that we'll talk about later, but these are the ones that we'll start off with. For example, word description followed by the roster method for the set of denominations of U.S. currency in production at this time. I just did a word description. It describes a set. In the roster method, you would actually list every bill of U.S. currency that's currently in production. There's a $1 bill, a $5 bill, a $10 bill, a $20 bill, a $50 bill, and a $100 bill. You would write them down with commas separating them inside of a pair of brackets. And that's called the roster method. The set of U.S. states bordering the Pacific. That's the word description of the set. The roster method would be to list each state individually, separated by commas inside of a set of brackets. And they are California, Oregon, Washington, Alaska, and Hawaii. So the ideas are simple. You can describe the set in words, or you can list the elements using the roster method. Here's an exercise. Use the roster method to represent the set of days of the week. Again, you simply list them with commas inside of braces: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Notice that I put them in a certain order, but in a set, order is not important. So had I scrambled those names up, it would not have mattered. It would still be the same set. How about this one? Write a word description for the set, capital A equals, and then inside of the braces, you've got A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. How would you describe that? Well, I would say A is the set of letters of the English alphabet. And I say the English alphabet because there are other alphabets besides the English alphabet, and they're not all the same. Because this is a math course, we'll be particularly interested in certain sets, and I'm going to mention a few of them now, and they're used extensively in many areas of mathematics. First of all, we have the natural numbers, sometimes called the counting numbers. We use a capital N when we're talking about those numbers, and it's simply the numbers we count with: 1, 2, 3, 4, 5, and the ellipses, the dot, dot, dot at the end just means that the pattern continues forevermore. The whole numbers, we use a capital W to represent that, and it is the same as the counting numbers with the exception of an addition of 0. So the whole numbers begin with 0 and continue through the counting numbers. The natural numbers or counting numbers do not include 0. Then we have the integers. We use capital I for that. And the integers, if you look in the middle at the 0, to the right you get the counting numbers. To the left of 0 you get the negatives of the counting numbers. And notice the ellipses, the dot, dot, dot in both directions. And that means the pattern continues infinitely in both directions. So the integers consist of 0, and to the right, 1, 2, 3, 4, 5, the counting numbers, and to the left, the negative of the counting numbers, -1, -2, -3, -4, and on and on. You might notice that the counting numbers are inside the set of integers. So counting numbers are also integers. So you could also say that the positive integers are the same thing as the counting numbers. There are a lot of little relationships like that that you could notice if you really wanted to. The rational numbers, we use Q for that. The rational numbers is the set of fractions which are formed as an integer divided by another integer as long as you're not dividing by 0. You can also define Q as a set of all terminating or repeating decimals. It turns out those two definitions are equivalent. The irrational numbers, we use a script I. A regular I for integers, a script I for irrational numbers. That's the set of all decimals that don't terminate and don't repeat. And finally, the set of real numbers, we use capital R. That's the set of all rational or irrational. If you throw the rational numbers and the irrational numbers together, you get the set of real numbers. And I also say that having defined real numbers, you can also go back and define the irrational numbers as a set of real numbers that are not rational. Couldn't really define it that way until I had talked about what rational numbers are and irrational numbers are. But once I've defined those terms, I can also talk about irrational numbers as real numbers that are not rational. Those are the kind of things that you'll need to have some familiarity with so that if a question uses those names, you'll know what it means. How about this? Use the roster method to write each of the given sets. The set of natural numbers less than 5. Remember, the natural numbers are the counting numbers, 1, 2, 3, 4, 5, 6, 7, and on and on and on. If you only want the ones less than 5, you've got to mark out 5 and everything to the right. So the natural numbers less than 5 consist of the set of elements 1, 2, 3, and 4. How about this? The solution set of the equation x plus 5 is equal to minus 1. If you take that equation and solve for x by subtracting 5 from both sides, you'll find out that x is equal to minus 6. So the solution set is the set containing the single element negative 6. And this one, the set of negative integers greater than minus 4. Remember, the negative integers are part of the integers. The integers, if you think of 0 as sort of being in the middle, to the right you get the counting numbers 1, 2, 3, 4, 5, and on and on. To the left you get minus 1, minus 2, minus 3, and so on to the right. If you're looking for the negative integers greater than minus 4, remember the negative integers, if you're moving to the right, stop at minus 1. Once you get to the right of minus 1, you're not in the negative integers anymore. But you only want the ones greater than minus 4. You also don't want to go to the left of minus 4 with things like minus 5, minus 6, and so on. So the set of negative integers greater than minus 4 has to be to the right of minus 4, but stop once you get to the last negative integer, which is minus 1, or the last negative integer before you get to 0. And remember, it didn't say greater than equal to minus 4, it just said greater than minus 4. So there are only 3 of them. The solution set is the set consisting of minus 3, minus 2, and minus 1. There's also a term called well-defined when we're talking about sets. A set is well-defined if it's possible to determine whether any given item is an element of the set. And the best way to illustrate it is through some simple examples. If I said the set of letters of the English alphabet is well-defined, you should say, yes, that's right, because I can tell you whether anything that you flash in front of me is in that set or not. But if I say the set of great songs is well defined, you might pause with that, because the set of great songs, how do you decide if a song is in it or not? Because what you think is great might not be what I think is great, and in fact, you might think one time that a song is great, and a year later you might think it's not. That's sort of just an opinion. It's not well defined. And that is the sense of what well defined means. If you can nail it down for sure that you can look at something and decide if it's in the set or not, that set is well defined. If there's any ambiguity, then it's not. There's a lot of notation in mathematics, and there's a lot of notation in set theory. If I give you the statement 4 is an element of the set of natural numbers, a mathematician is going to want to write that in a more condensed format. We use a lot of symbols. We use the symbol, sometimes I call that the pitchfork symbol, and it means is an element of. I would write 4 and then write the symbol for is an element of, and capital N is the letter we use for natural numbers. And I would read that symbol as is an element of. If I wanted to state that something's not an element of a set, we take that same symbol and put a slash through it. So in order to write minus 3 is not an element of the set of natural numbers, I would take the symbol for it is an element of and put a slash through it, and I would say minus 3 is not an element, by putting the slash through there, of the set capital N, which represents the set of natural numbers. So it's standard to put a slash through a symbol to mean not. Determine whether each statement is true or false. A says 4 is an element of the set containing the elements 2, 3, 4, and 7. It's true if there is a 4 in that set, and there is, so it's true. B, minus 5 is an element of the natural numbers. Remember, the natural numbers are the counting numbers. Negative 5 is not a counting number. If you look in that set, you don't see negative 5, so that's false. C says 1/2 is not an integer, is not an element of the set of integers. Remember, the integers have 0, and then to the right the counting numbers, and to the left the negative of the counting numbers. 1/2 is not in there at all. If you look, there is no 1/2 in there, so it's true that it's not an element. Got to be careful, that symbol says not an element of, so it's true that 1/2 is not an integer. And finally, D, the set of nice cars is a well-defined set. Is that true or false? Well, again, very similar to what I said earlier with the example about songs. That's sort of an opinion question. It is not well-defined, so the set of nice cars is definitely not a well-defined set. We also talk about the empty set, or sometimes we say the null set. It's the set that contains no elements. We use two different symbols pretty regularly to stand for the empty set, and that's a circle with a slash through it or a pair of braces with nothing inside. You'll see both of those symbols, so if you see either one, you'll know that we're talking about the empty set. As an example of the empty set, consider the set of natural numbers that are negative integers, or the set of birds that live at the bottom of the ocean. There simply aren't any natural numbers that are negative because natural numbers are counting numbers. There are no birds, as far as I know, that live at the bottom of the ocean. Those would both be simple examples of empty sets. Now, I talked about earlier there were two common methods of writing sets, and that is to do it in words or to use the roster method. There's actually a third method, which in a sense is a combination of the two. It's called set builder notation. Set builder notation is especially useful when you describe infinite sets, or things that are hard to write out as well. In set builder notation, the set of natural numbers greater than 7 is written as follows. You put your braces on left and right, and then you write, and you don't always have to use the letter X, but it's quite common, X, then a vertical line, followed by X as an element of capital N, which is the natural numbers, and at the same time, X is greater than 7. So this is sort of a combination between writing it in words and writing it out element by element. You're using words, but you're also using components of the roster method, in particular the braces. Here's how you should read this. The opening left brace should be read as the set, and the X should be read of all elements X. So you're reading left brace X as the set of all elements X. The vertical line is read as such that. Then you've got the next part which says X is an element of the natural numbers, or X is an element of the set of natural numbers, and X is greater than 7. So you move across from left to right. The opening brace is read the set. The X is read as of the set of all elements X. The vertical line is read such that, and you just keep reading across. It's simply impossible to list all elements of the set because there are an infinite number of them, but set builder notation precisely defines the set by describing its elements. For example, let's use set builder notation to write the following sets. The set of integers greater than -3. So you could write X and use the symbol for is an element of. Capital I is integers, so X is an element of the integers. In other words, X is an integer, and it's greater than -3. Takes a little practice, but once you get used to it, you simply read that out to yourself, and you've got an idea of what the set really is. And another one, the set of whole numbers less than 1,000. So you start writing out opening brace, X, vertical line. That's the set of all X such that X is a whole number. Remember, capital W stands for the set of whole numbers. So you write X with the symbol for is an element of. X is an element of the whole numbers. And X is also less than 1,000. Practice makes perfect here. Practice will help you see, after you've done a few, how it works. Another definition. A set is finite if the number of elements in the set is a whole number. For example, if I said the set containing the elements 1, 3, 6, and 7 is blank, and I want to put finite if it's true or not finite if it's false, because it has 4 elements and 4 is a whole number. Remember, a set is finite if the number of elements in the set is a whole number. Well, it does have 4 elements, and 4 is a whole number. A finite set, you can count how many elements are in there. And you say whole number instead of counting number because you could have the empty set, which would have 0 elements. Conversely, if I take the set containing 1, 3, 5, ... which means it continues forever, you never get to an end, so you can't count them and get a whole number answer. So that means that set is not finite because it has an infinity of elements, and infinity is not a whole number. Another definition. The cardinal number of a finite set is just the number of elements in the set. Just a fancy way to say how many elements are in the set. The cardinal number of a finite set is denoted n of a. Little n, and in parentheses the name of the set. So that would be read n of a. So the cardinal number of a finite set is the number of elements in the set. For instance, if the set A is a set containing 1, 3, 6, and 7, then the number of elements in A is 4. Another way of saying that is the cardinal number of the set A is 4. You could also say that A has a cardinality of 4. Let's find the cardinality of each of these sets. J is a set containing 2 and 5. Well, that's easy enough. There are only 2 elements in that set, so the cardinality is 2. You could also write n of j is equal to 2. Now, before I do the next one, I want to mention something that's useful in answering this next question. There is a formula for counting elements in a big set if the elements are consecutive integers. So you can kind of guess the next example I'm going to do is with consecutive integers. If you had a set containing the elements 7, 8, 9, all the way to 22, or something like 4, 5, 6, 7, 8, 9, 10, all the way up to 45, there's an easy way to count those, and that is to use this formula. The number of elements in a set of consecutive integers is simply the biggest number minus the smallest number plus 1. So for that 7, 8, 9, all the way to 22, you would take 22 minus 7, the biggest one minus the smallest one, and add 1. And that would come out to be 16. If you don't believe me, count them out and see. There are actually 16 elements in that set. If I took the 4, 5, 6, to 45, it would be 45 minus 4 plus 1, and that comes out to 42. This only works for consecutive integers, though. If they're not consecutive, you can't use this formula. With one exception. Sometimes you have a set with a pattern that can be shown to have the same number of elements as another set that does have consecutive integers. For example, if I ask you to find the cardinality of the set 6, 9, 12, 15, all the way to 33, those are all multiples of 3. 6, 9, 12, 15, they're all divisible by 3, so those are all multiples of 3, all the way to 33. Those aren't consecutive, so you'd say, well, you can't use that formula above because they're not consecutive. And that's true enough. But if the numbers have a certain pattern, you might be able to associate that set with another set that is consecutive that has the same number of elements. And the trick of that is try dividing every element by 3 and look what happens. If you divide 6 by 3, you get 2. If you divide 9 by 3, you get 3. If you divide 12 by 3, you get 4. If you divide 15 by 3, you get 5, all the way to the end. And look, those numbers are consecutive, 2, 3, 4, 5, to 11. And they have the same number of elements as the original set because all you're doing is dividing everyone by 3. You're not changing how many there are. But now that you know that 2, 3, 4, 5, to 11 has the same number of elements, and they are consecutive, I can use the formula for the consecutive one, biggest minus smallest plus 1. That's 11 minus 2 plus 1, which is 10. So if the set containing 2, 3, 4, 5 all the way to 11 has 10, then the one that I was really looking at originally must also have 10. So there's sort of a trick there when you have multiples. If you divide out the multiples, you get consecutive integers, and you can use the formula on those. You can kind of guess the next example I want to work uses that idea. So the next example is the set S containing 3, 4, 5, 6, to 31. Those are consecutive, so you can say 31 minus 3, which is 28, plus 1 is 29. You could also write n of S is equal to 29. The cardinality of that set is 29. Now, this one, the set containing 3, 3, 7, 21. That's basically a trick question. You really should not list the same element more than once in a set. But if you do, you don't count it more than once. So even though that 3 got listed twice, 3, 7, and 21 are the only elements of that set. Just be on your toes. Occasionally they'll throw something in like that to make you think. But if an element is written down more than once, it's only counted once. So the cardinality of that set is 3, and you could say n of t is equal to 3. We also talk about equal sets. A set A is said to be equal to a set B, and you actually use an equal sign. You denote that A equals B, if and only if A and B have exactly the same elements. So if I gave you the set containing D, E, and F, and asked you to compare it to the set containing E, F, D, you could say that they're equal because they have the same elements. There's a D in both, an E in both, and an F in both, and there's nothing that's in one and not the other. Remember, the order of sets does not matter. But if I ask you to compare the set containing D, E, and F to the set containing D, E, and T, those sets would not be equal because there's a D in both, there's an E in both, but there's an F in one and not in the other, and there's a T in one and not the other, so those sets are not equal. They have to have the exact number of elements, and they have to be the same elements. There's a looser term called equivalence. Set A is said to be equivalent to set B, and instead of putting an equal sign, you put a tilde, or sort of a squiggle. That represents equivalence. A is equivalent to B if and only if A and B have the same number of elements. If you use that notation we developed earlier, you can also say A is equivalent to B provided that the number of elements in A is equal to the number of elements in B. In other words, you're simply counting. You don't care what the elements are, they just have to be the same number in both. Equality, they have to be exactly the same elements. Equivalence, they just have to have the same number of elements. So for instance, the set containing D, E, and F is equivalent to the set containing E, F, and D. You could have used equal there because they have exactly the same elements, but they're also equivalent. But the other one, D, E, and F compared to D, E, and T, they're not equal because one's got an F and the other's got a T. But they are equivalent because there are 3 elements on the left, D, E, F, and there are 3 elements on the right, D, E, T. So you're simply counting when you're looking at equivalence. Today, as we continue our study of sets, let's talk about complements, subsets, and Venn diagrams. I want to begin by talking about something called the universal set and its complement. The set of all elements that are being considered is called the universal set. We'll use the letter capital U to denote the universal set. For example, if we were doing a survey on the month in which a person was born, then the universal set would be the set containing all 12 months: January, February, March, April, May, June, July, August, September, October, November, December. There are no more months to consider. That would be our universal set from which a particular month would be chosen for a particular person. The complement of a set A, denoted by A with an accent symbol as a superscript, is the set of all elements of the universal set U that are not elements of A. So you can't define the complement of a set until you know what the universal set is. For example, if the set J is a set containing January, June, and July, then the complement of J would be you go up to the universal set and you cross out the elements of J, which would be January, June, and July. That happen to be the months that start with the letter J. And what you're left with is the complement of J. So the set containing J complement is a set containing February, March, April, May, August, September, October, November, December. Let's try this example. Suppose the universal set that we're interested in is the set containing the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The set S is the set containing the elements 2, 4, 6, and 7. And the set T is written in set builder notation. It's a set of all X such that X is less than 10 and X is an element of the odd counting numbers. Two things we want to find here. Part A, we want to find S complement. So let's look at S complement first. in order to find the complement of a set, you have to know the universal set. So when we're looking at the complement for the set S, we have to go back up to the universal set and cross out any elements that are in S, and whatever's left is in the complement. So the elements that didn't get crossed out are 1, 3, 5, 8, 9, and 10. So S complement is the set containing the elements 1, 3, 5, 8, 9, and 10. Now let's move to T complement. First of all, I noticed that T was written in set builder notation, so the first thing I would do is write out T explicitly before even thinking about forming the complement. So we need to know what those elements are explicitly. So we're looking for the numbers less than 10 that are inside the universal set. That would be the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. But we also want those to be counting numbers that are odd. In other words, the numbers that are less than 10 and odd. If you look at the numbers that I have put in the rectangle indicating that they are less than 10, the odd ones are 1, 3, 5, 7, and 9. So written out explicitly, T is simply the set containing the elements 1, 3, 5, 7, and 9. Now you've done all this work, but we only found T. We want to find T complement, so don't forget, you've only found T now. We wrote out T explicitly. T complement is found by going back to the universal set and crossing out every element of T. If you do that, you cross out 1, 3, 5, 7, and 9. You're left with 2, 4, 6, 8, and 10. So T complement is the set containing the elements 2, 4, 6, 8, and 10. Just need to practice. There are two fundamental results concerning the universal set and the empty set. First of all, because the universal set contains all elements under consideration, the complement of the universal set then has to be the empty set. The complement of everything would be nothing. Secondly, the complement of the empty set is a universal set because the empty set has no elements and the universal set contains all the elements. So the complement of nothing is everything. The complement of everything is nothing. The complement of nothing is everything. If we want to do this symbolically, I could write U complement is equal to the empty set. And remember, there are two common symbols for empty set. The circle with the slash through it and the braces with nothing in it. So if I'm looking back at that first result, the complement of the universal set is U complement. It's equal to the empty set. Now you don't have to write both of those symbols. I'm just writing them both for completeness because you see them both occasionally. You need to know that if you see either one, it means the empty set. The complement of the universal set is the empty set. That's the symbolic way of writing it. And the complement of the empty set, whichever way you write it, either the open circle with a slash through it or the braces with nothing in it, the complement of the empty set is the universal set. And remember that I don't have to write both of those symbols for the empty set. I just write one or the other. I'm writing both for completeness here. Let's talk a little bit about the concept of subsets. Consider the set of letters in the alphabet and the set of vowels, the set containing A, E, I, O, and U. Every element of the set of vowels is an element of the set of letters in the alphabet. Having said that, the set of vowels is called a subset of the set of letters of the alphabet. We'll often find it useful to examine subsets of a given set, so this is an important concept. Formally, a set A is a subset of set B, denoted by, and you see the symbol, it's the set A, and then the symbol is a sort of a sideways U opening to the right with a bar under it. A is a subset of B, if and only if every element of A is also an element of B. Just like I was talking about, the set of vowels is a subset of the set of letters of the alphabet because every vowel is also a letter. Here are two fundamental subset relationships that I want to emphasize. A is a subset of A. In other words, a set is a subset of itself by definition. And the empty set is a subset of A. And this is true for any set A. A set is a subset of itself, and the empty set is a subset of every set. So every set automatically has a subset equal to itself and the empty set. As we've done with other symbols in this course and in previous courses, if you put a slash through a symbol, it typically means not. A is not a subset of B, and look at the symbol. It's the subset symbol with a slash through it. It means that A is not a subset of B. To show that A is not a subset of B, we must find an element of A that's not an element of B. So if you want to show something is not a subset of something else, you have to find an element in that set that's not in the set that you're claiming it's not a subset of. Let's look at this and do some true-false. If I ask you, is this true or false? A set containing 5, 10, 15, and 20 is a subset of the set containing 0, 5, 10, 15, 20, 25, 30. All you have to do is start on the left and element by element look for that same element on the right. So you notice that the 5 inside the left set is in the right set, 10 from the left set is in the right set, 15 from the left set is in the right set, and 20 from the left set is in the right set. That's what you need to show that something's a subset of another set. So that statement is definitely true. How about this? W is a subset of N. Remember, W, the capital W, is the symbol for whole numbers. The whole numbers are the counting numbers with 0 thrown in. So it's the set containing 0, 1, 2, 3, 4, on and on in that pattern. The natural numbers is the letter N. The natural numbers are the counting numbers. They start with 1. 1, 2, 3, 4, ... which means it continues in that pattern. So you have to look at each element on the left and see if you can find a match on the right. And the very first thing you look at, which is a 0 on the left, does not have a match on the right. That means the statement is false. The whole numbers are not a subset of the natural numbers. How about this? The set containing 2, 4, 6 is a subset of the set containing 2, 4, 6. Now remember, we just talked about this. Every set is a subset of itself. And if you see, by doing the same thing we did for the others, there's a 2 on the left, it appears on the right. There's a 4 on the left, it appears on the right. There's a 6 on the left, it appears on the right. Therefore, it is true. But anytime you see a set compared to itself, a set is always, by definition, a subset of itself. How about this? The empty set is a subset of the set containing 1, 2, and 3. Now, if you remember what I said just a few minutes ago, you'll have this immediately, and that was the empty set is a subset of every set. So it doesn't really matter what's on the right. If you've got the empty set with the subset symbol, whatever you put on the right, it's going to be a true statement because the empty set is a subset of every set. That statement, therefore, is true. The English logician John Venn, who lived from 1834 to 1923, developed diagrams which we now call Venn diagrams that can be used to illustrate sets and relationships between sets, and I find them extremely useful, and I think you will too. In a Venn diagram, the universal set is represented by a rectangular region, and the subsets of the universal set are represented by oval or circular regions inside of the rectangle. This Venn diagram in particular shows a universal set U and one of its subsets A. The region outside of the circle but inside of the rectangle is the complement of the set A. So A is the set represented by the circle itself. A complement is represented by the area outside of the circle. We talked about subsets. Now I want to talk about something called proper subsets. A set A is a proper subset of a set B if every element of A is an element of B, and additionally, A and B are not equal to each other. It's the same symbol as for subset without the bar. Think about this in a minute. The definition of a proper subset is exactly the same as the definition of a subset, except that it doesn't allow the sets to be equal. With subsets, we said a set is always a subset of itself. With a proper subset, a set is never a subset of itself. In fact, the only difference between the definitions of a subset and a proper subset revolves around whether or not the entire set is included or not. If the entire set is included, you can call it a subset. You can't call it a proper subset, though. Now remember, for a subset, we already know that every set is a subset of itself. If you had the set B, you could say B is a subset of B. You could say that the set containing 2, minus 1, and 7 is a subset of the set containing 2, minus 1, and 7, and on and on. But for a proper subset, that's not the case. It does not allow equality. It's the only difference between subset and proper subset. So for instance, whereas above I could say B is a subset of B, B is not a proper subset of B. And above where I said the set containing 2, minus 1, 7 is a subset of the set containing 2, minus 1, and 7, I have to say that the set containing 2, minus 1, and 7 is not a proper subset of the set containing 2, minus 1, and 7. Only that one single difference. Once you think about it, it should be easy enough. Do a couple of examples. Is the set containing A, E, I, O, U a subset of the set containing E, I, O, U, A? Remember, in sets, order doesn't matter. All you have to do is look. There is an A on the left that reappears on the right. There's an E on the left that reappears on the right. Same is true for the I, the O, and the U. So that is true. Yes, that is a true statement. How about this one? Is the set containing A, E, I, O, U a proper subset of the set containing E, I, O, U, A? Now remember, those are the same two sets. I just changed the symbol. So I know those two sets are equal from my previous work. But for a proper subset, you can't have equality, so that's automatically going to be no. The set on the left is not a proper subset of the set on the right because they're equal, and a proper subset, and with proper subsets, that is not allowed. How about this? Is capital N a subset of capital I? Remember, capital N is the symbol for natural numbers, so that's the set of counting numbers. Capital I is a set of integers. That includes the counting numbers, but it also includes 0 and the negatives of the counting numbers. So if you look on the left, everything on the left has a counterpart on the right. So yes, the set of natural numbers is a subset of the set of integers. Is the set of natural numbers a proper subset of the set of integers? Well, yes, because there's no equality. You can see that there are elements of integers that are not elements of the counting numbers or the natural numbers. So it is also true. Yes, the set of natural numbers is a proper subset of the set of integers. Let's list every subset of this set. Say we have a capital C set, which maybe C stands for condiments, and the elements are mustard, ketchup, onions, and relish. Starting off with the empty set, because we've already discussed that the empty set is a subset of every set. That's the only subset that doesn't have any elements. Now let's move up to the one element subsets. We just take each condiment one at a time and put it in a set. So you start off with mustard, you do ketchup, you do onions, you do relish. That's all the possible subsets with just one element. Now let's move to the two element subsets. You have to have some organized pattern here. So I'm going to start with mustard and match it with every other condiment. So I'll say mustard ketchup, then I'll say mustard onions, then I'll say mustard relish. I've matched mustard with every condiment. Now I'll move over and do the same with ketchup. I've already matched ketchup with mustard, so now I'll move to ketchup with onions and then ketchup with relish. Now I've matched ketchup with every condiment, so now I'll move to onions. Well, the only condiment I haven't matched onions with is relish, so I match onions with relish. Now let's move to the 3-element subset. The easiest way to think about this, there are only 4 elements in the whole set, so you'll get a 3-element subset by eliminating a condiment each time. So if I eliminate relish, I get mustard, ketchup, onions. If I eliminate onions, I get mustard, ketchup, relish. If I eliminate ketchup, I get mustard, onions, and relish. And if I eliminate mustard, I get ketchup, onions, and relish. And I claim that the only remaining subset is the 4-element subset consisting of the set itself. In other words, all of them. So how many subsets does that represent? If you count them, you'll find out that a 4-element set has 16 subsets. If I change it to proper subsets, remember the only difference is whether the set itself is a subset. So if I'm doing proper subsets, I have to leave out the set itself, so the 16 drops down to 15. So if I'm counting proper subsets, there are only 15. It's always true that the number of proper subsets is 1 less than the number of subsets. Let's see if we can find a pattern here. We know that a set with no elements has only 1 subset, namely the empty set, and that a set with 1 element has 2 subsets, namely itself and the empty set. And although we haven't done it, it's easy to show that a set with 2 elements has 4 subsets, and a set with 3 elements has 8 subsets. We just discovered that a set with 4 elements has 16 subsets. Let's see if we can devise a pattern. If you look at this following information in table form, you can see that if a set has no elements, it has 1 subset, 1 element has 2 subsets, 2 elements has 4 subsets, 3 elements has 8 subsets, 4 elements, 16 subsets. I'm looking for a pattern here. Do you see one? Do you see something that might be a possible pattern? Notice that each one of those number of subsets is a power of 2. 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 to the 2nd, 8 is 2 to the 3rd, and 16 is 2 to the 4th. It seems as if the number of subsets is 2 to the power of n, where n is the number of elements. Although we've not proven that that pattern continues, it turns out that it does. So we have the following result. A set with n elements has 2 to the power of n subsets. And because we already know that the number of proper subsets is 1 less than the number of subsets, we also have this result, which says that a set with n elements has 2 to the power of n minus 1 subsets, 1 less. Let's look at this example. Suppose a restaurant sells pizzas for which you can choose from 7 toppings. How many different variations of pizzas can the restaurant serve? Think about this. You could have a pizza made with no toppings. How yucky would that be? Or 1 topping, or 2 toppings, or 3 toppings, or 4 toppings, or 5 toppings, or you could say put all 7 toppings on there. Well, that just means we're looking at toppings as elements of a set, and we're looking at how many subsets of toppings can you have on your pizza. So there's an analogy there between subsets of a set and subsets of toppings to be put on the pizza. That means there are going to be 2 to the 7th, which is 128 variations of pizza from this restaurant if you count a no-topping pizza. So you could have a pizza with nothing on it. You could have pizzas with just 1 topping, pizzas with just 2 toppings, 3 toppings, and you can see that's just like counting subsets. So this idea of subsets can be very useful in counting problems. Relating this back to your calculator, you're going to be using the calculator a lot in this course, so you need to start learning how to use it. There's a button, which I call the power key. It has an X with an exponent of Y, and that's your power button. So if you wanted to find out what 2 to the 7th was in the most efficient way, you would enter 2 into your calculator, press the X to the Y key, type in 7, and then press equal, and that would give you 128. How about this? What is the minimum number of toppings the restaurant must provide if it wishes to be able to advertise that it offers over 1,000 variations of its pizzas? Well, first of all, we know that 7 toppings is not enough because 7 toppings only produce 128 different variations of pizza. So that's not big enough. So my suggestion is you just start off knowing that 7 is not enough and keep going up until you pass 1,000. So if you do 2 to the 8th, you'll find out that's 256. That's not enough. If you do 2 to the 9th, you'll find out that's 512. That's not enough. But when you get to 2 to the 10th, you finally passed 1,000 variations of pizza. Restaurant would have to have at least 10 toppings before it can legitimately advertise that it can provide over 1,000 variations of its pizzas.
Okay, so 2.2, so last section for today. All right, so we talked about sets, we talked about types of numbers and things, and so now section 2.2 is about complements, subsets, and Venn diagrams. So the reason complements and subsets are being talked about in the same section is because of this idea. Complements are sets outside of other sets, and subsets are sets inside of other sets. So it's 2 reverse ideas, and that's why they're being lumped together in the same question, or same section rather. Okay. All right, so the first thing we have to talk about before we talk about complements or subsets is the idea of the universal set. So the universal set is the set of all elements being considered in a certain context. So in other words, it's the, quote, universe of the problem. So it's the only things that we care about for that specific scenario. Okay. So, for example, if you're talking about the grades in this class, the universal set, which we call U, is going to be any of the grades that you could get in this class. So, A plus, A minus, same thing with B's, so B plus, B minus, and then C plus, C minus. And then this class is an NC class. So there's passing and then not passing, basically. So for this class, if we were talking about the universal set of grades, that would be the universal set. If you were in another class, they might include like the D grades and then F instead. At my school, plus and minus grades were optional, so most professors didn't have minus grades or plus grades. Some of them had plus, but basically it's just what do you care about in this specific context, okay, which will be significant for the next definition. That's weird. Okay, we're just going to ignore that random curly bracket. Okay, so definition of complement. So I said that complements were sets outside of other sets. And so the complement of a set A, which is denoted A prime, and I'm going to use colors here, is the set of all elements of the universal set that aren't in A. And so a visual is probably helpful for this. So the universal set is usually just going to be denoted by like a box, and everything inside the box is your universe. So if A is this circle, here's the set A, then anything outside the circle is going to be A prime. Okay, so A prime is everything outside of A. So sets outside of other sets. Okay. So if you can remember the visual, you've got your set A, and then A prime is everything else, everything that you didn't account for. So for example, let's say your universal set is 1, 2, 3, 4, 5. Those are the numbers that you care about. And A is the set 1, 2. So if you were asked to find A prime, then A is 1 and 2, and you want everything else. So in the universal set, you don't want 1 or 2, you want everything other than that, which would be 3, 4, 5. Okay. Another quick example, if the universal set is just 1, 2, 3, and A is the same set, then the complement would be everything other than 1 and 2, which would just be 3. Okay. So the reason for giving this example is because it's just to illustrate that if the universal set is different, then even when the set A is the same, the complement will change. Okay, we have two sets that were not equal here. So the universal set is significant. So you always want to start with what's the universe of the problem and then go from there. Okay. So any questions there? Okay. All right, so complements is everything other than, basically. So let's do a couple examples. Okay. All right, so first example, find the complement of the set of even natural numbers less than 7, given that U is the natural numbers from 1 to 10. Okay. So the first thing that you want to do, since they haven't nicely written out what your starting set is, you just want to write that out. So using the notation from the past couple examples, this set of natural numbers less than 7, let's just call that set A. And so the first thing you'll want to do is write out what that set actually is. So A is the even natural numbers. So we're not going to count 0, even though it's even, because that's not a counting number. So we'll start with 2, and we want to be less than 7, so we'll go up to 6. Okay, so that is A. And now we want A prime. And A prime will be everything else. Okay. So A is 2, 4, and 6. So in the universal set, we're not going to count 2, 4, and 6 because those are already accounted for. So A prime will be all the other stuff that we didn't cross out. So 1, 3, 5, and then 7, 8, 9, 10. Okay. So usually when I'm doing this, I cross out the numbers that are in the set and then just write everything else. Okay. So any questions on that one? Okay, so if they don't give you the set explicitly, then you just want to write it down first. Like figure out what the actual set is. All right, So next example, and then I'll let you guys do one on your own. So find the complement of this set given that the universal set is something in set builder notation. So we're going to have to interpret each of those sets. So it's going to be helpful first to write out what the actual sets are. So U in raster method notation, it's everything in between -2 and 6 integer wise. So you start with -2 and keep going. So -1, 0, whoops, 1, 2, 3, 4, 5, 6. Okay. A is our original set, so here's A. And A is the natural numbers, so starting with 1 and less than or equal to 5. So 2, 3, 4, 5. Okay. And now you want A prime. A prime is everything else. So now that you have what the actual sets are, you just cross out what you've already accounted for. So 1, 2, 3, 4, 5 you already have. And so A prime is everything else. -2, -1, 0, and then 6. Okay, so if you're asked to find complements, it's usually helpful to write out everything in the relevant sets if they haven't done so already. And then just the complement is everything else, everything that you don't already have. Okay. All right. So let me go ahead. This is the last poll for the day. Okay. So one more question like this. So find, hello. I tell you what, my luck this whole semester has not been great. Okay, so let me copy out. I apparently don't have everything here, but find the complement of the set. X is in the integers and zeros, given that U is 0 through 10. I'm not sure why it didn't pop up, but this is what the question should be. Okay, so take a couple minutes to think about that, and then we'll go back over it. Okay, so real quick, going over this one, you just have to, again, write out what you have. So A is everything between 0 and 3, but you don't include the 3. You're less than 3. So A is 0, 1, and 2. And you want to be less than 3, so you stop there. And so if you cross out those numbers, A prime is everything else, which is 3 through 10. So 3, 4, 5, 6, 7, 8, 9, 10. Okay. So make sure that you don't stop partway. You're not just finding A. You're using A to get everything outside, everything other than A. Okay. So any questions there? Okay. All right. So moving on. All right. So that was complements. So this section is two things, complements and subsets. So we've got one more topic. And then we're done for the day. So definition, set A is a subset of set B. There's the notation. It's like a sideways U thing. And you can kind of think of that notation as being like the less than or equal to notation. And set A is a subset if every element of A is also an element of B. So easiest thing to do is draw the picture again. So if here's A and here's B, then A is inside of B. Or you can think of it as B contains A. Okay, so here's the visual for subsets. A is a subset of B if it is inside of B. So complements was everything outside of A, whereas subsets is the idea of being inside another set. So example, 1, 2, 3 is a subset of the real numbers. Because 1, 2, and 3 are all real numbers. And A, E, I, O, U, that is a subset of the alphabet, because those are all inside of the alphabet. Okay, so nothing too earth-shattering with those examples. Okay, so subset is being inside something else. Okay. All right. So, couple examples here. Okay. All right. So let U, our universal set, be J, Q, K, and A. I'm picking this as the non-numbered cards in the deck of cards. Okay. And S is the set J, and T is the set Q, comma, K. And you want to figure out whether these are true or false. Okay, so first one is S a subset of T? Okay, so it's probably easiest to write out what the set is first. So S is the set J, and T is the set Q, comma, K. Okay, so you're asking, is J inside of Q and K, which is clearly false. They're not even related to each other at all. So that is not true, and the statement is false. And so the notation for that, the notation for not being a subset of, would be S not subset of T. So just the dash through it. So S was not inside of the second set. All right, so next example, is T a subset of S prime? Okay, so T is the set Q, comma, K, and S prime is everything outside S. So if S is J, then S prime is Q, K, A, right? So what you're asking is Q, K a subset of Q, K, A? Which it is, right? So this is true because Q, K is inside the other one. So this works, and this is true. Okay. So same kind of thing as with the complements examples. It's easiest to just write out the elements of the sets in question and then answer. So we wrote out the specific elements in each set, and then it was easy to see whether the statement was true or false. All right, so last example of this type. Same sets, but now we're answering T subset of T. So T is the set Q, comma, K. And you're asking, is QK a subset of QK? Or is QK inside of QK? And this is true, because yes, everything inside the first set is inside the second set. And really, it's kind of silly, but any set is a subset of itself. Okay, so yes, it's true that the alphabet is a subset of the alphabet. Yes, it's true that spring, summer, fall, winter is a subset of the set of all 4 seasons. But these aren't very interesting sets. It's not really probably what we want to talk about most of the time. And so there's sort of an adjustment of our definition of subset. So set A is a proper subset of set B. And I think of proper in the sense of legit. If A is a subset of B, but it's not that stupid case where they're actually equal. So it's something smaller than B. So the notation, you can kind of think of it as like the less than notation. So yes, it's true that any set is inside of itself, but that's kind of dumb. So if you're trying to talk about something more interesting than that, and you want something that's genuinely inside of another set, then you talk about the proper subsets. So not equal. Okay. All right. So any questions there? Okay, we are so close, I promise. So we have 2 last questions we have to answer about sets. So the first one is to list all of the subsets of a set, to figure out what are all of the things that are contained inside of a set. And then the other question is to find the number of subsets. So let's do one example where you're listing subsets. Okay. So there's lots of ways to do this. It's kind of like the very first section we did where you were listing out possibilities. It really doesn't matter how you do it, but it helps to be organized no matter what you do. Okay? So if you're listing subsets, you know that the sets will be inside of these. So at the very most, they'll contain M, A, T, and H. So any subset will have at most 4 elements. And so what you can do is just list out any set that has 0, 1, 2, 3, or 4 elements. So any subset will have at most 4 elements. Okay. So the 2 easy subsets are the extreme cases. So to have 4 elements, to have 4 elements, you just have to have everything. So M, A, T, and H. And to have no elements, that is a subset because it is inside of any set. So 0 elements means the empty set. So that case is easy to forget, but it is true that nothingness is inside of any set. Okay. All right. So you've always got nothing and everything as options, and then you just have to fill in the rest. So to have 1 element, that's just the individual letters. So you have the set M, the set A, the set T, and the set H. Those are subsets. And now you have to figure out a way of getting all of the possibilities with 2. So the way my thought process goes is I take the first letter, M, and pair it with everything else. So M goes with A, M goes with T, and M goes with H. So what I've done here is pair M with the other letters. Okay. And then that's some of my options. Now I have to pair A with all the other letters. So I've already got A with M, but I don't have A with T or A with H. Okay. So now I've paired M with everything, I've paired A with everything, but I haven't paired T yet, so I have one last thing, and that's T with H. Okay, so my thought process here is pair each letter with every other letter, and that's what I should get. Any questions so far? This is as bad as it will get. The more elements you have, the more annoying this is to do, so you shouldn't have to worry about more than 4. Because more than 4 will get really cumbersome to do. Okay. All right, so last case is having 3 elements, and my thought process is to omit one at a time. So I'll omit H, and I'm left with MAT. And then I'll omit T, and I'll just have MAH. And then I'll omit, wow, my curly brackets are getting kind of bad. I'll omit A, and I have MTH. And then I'll omit M, and I'll just have ATH. So what I'm doing here for this one is omit H, omit T, etc. Okay, so leave out one at a time. Okay. All right, so if you're asked to list all of the subsets, you have to remember you've got the empty set and the full set always. Those are always options. And then everything in between. And you just have to figure out a way of organized counting. So getting all of your options. Okay. So the second type of question we were going to ask was how many elements are there? Or how many subsets are there? So if we count, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there were 16 options in this example. And I'll just sort of point off to the side. This set had 4 elements. And 16 is equal to 2 to the 4. Which leads us into the last question for this section, which is a theorem. A set with n elements has 2 to the n subsets. So if you have n elements, then the number of subsets will be 2 to the n, like in the last example. And the logic for this, I'll do it really quickly. You actually can kind of figure this out already. So if you have a set with n elements, then each of the n elements has 2 options. Either to be or not to be. So to be in the subset or not. Okay. So each of the n elements in your set, it's either going to be something that you pick to be in the set or something that you leave out of the set. And so basically the reasoning for why this works is the counting principle from last section. So you have n slots for each of your elements. in each slot you have 2 options. And so you multiply it 2 times 2 times 2 times 2 times 2 n times, which is 2 to the n. Okay, so this formula isn't really anything new. It's just an application of the counting principle. Okay. So, doesn't come out of nowhere. Okay, so, last 2 examples here. Find the number of subsets. Fun fact, facetious is the only word in the English language that has all of the vowels singly and in order. And if you count Y as a vowel, then facetiously works. So, all right, so find the number of subsets. So we're just going to use the 2 to the n formula. So you have to count the number of elements. So this word has 9 letters in it. So the set has 9 elements. And so the number of subsets is 2 to the 9, which is 512. Okay. So, like I said, you would not be asked to find the number of subsets, or sorry, the full list of subsets for anything more than 4. Because even having 5 elements would mean 32 subsets, which is way too many to actually list out. So it grows very quickly. Okay, so the number of subsets, if you actually went through and listed every single possible option, you would have 512 total. And so part B is a small adjustment. Now you're only specifying the proper subsets. So the quote legit ones. So all you're doing is excluding the option of the whole set. The whole set, facetious. And so your final answer there would just be 512 minus 1, which would be 511. So the number of proper subsets is always just 1 fewer than the number of all the subsets. Because saying that it's proper just means that you're taking out the one option of having all the letters. So back in the last example, if you said it had to be proper, it would just mean you don't count the MATH option, and so you'd have 15 subsets that are proper. So that's the only adjustment there. So any questions on that? So if you're asked to find the number of subsets, you just remember the 2 to the n formula. Okay, so word problem. So let's say a restaurant sells pizzas for which you can choose from 7 toppings, okay, pepperoni, extra cheese, whatever. How many different types of pizza can the restaurant serve? So this is like a hidden subset question. So really what you're looking at is you are looking for the number of subsets of the set of 7 toppings, right? Because you have 7 toppings, and the different types of pizzas are going to be picking subsets of those toppings. Most people don't pick 7, they pick like 2 or 3. Okay. So really, you're just using the 2 to the n formula. So the number of types of pizzas will be 2 to the 7, which is 128 types. Okay, so it's a word problem, but it's really just asking for a number of subsets. What are the numbers of different ways you can pick from 7 toppings? We really could have done this in chapter 12 with the counting principle. It's just 2 to the 7. So you'd have 7 slots for your 7 toppings and 2 options for each slot. Okay. So that's the first part. It's just how many different types can you have with 7 toppings? And then a slightly different question. What is the minimum number of toppings the restaurant must provide if it offers over 1,000 types of pizza? So in the last example, you knew the number of toppings, and that was going to get you the number of subsets. And this one is the opposite. So we have the number of subsets instead. So we want 2 to the n to be at least 1,000. So if 2 to the n is the number of subsets, that's number of subsets or number of types of pizza, we want that, we want that to be at least 1,000. Okay, let's go back here. Okay, pizza. So this one is kind of just trial and error. You want 2 to the n to be at least 1,000, so you just start writing powers of 2. And you may as well start with what you got in the last part, which was that 2 to the 7 is 128, which clearly is too small to be 1,000, so that's not right. So we'll just go up by 1. So let's say you had 8 toppings. The number of types of pizza would be 2 to the 8, which is 256. Still too small. Okay. So just trial and erroring it. 2 to the 9th is 512, which is also too small. But 2 to the 10th power is 1024, which is bigger than 1,000. And so this works. So your answer then would be 10 toppings. Okay, so if any of you played that 2048 game from a few years ago, this would be relevant because it has the powers of 2. So for this example, they give you the number of toppings and you're trying to find n. So the easiest thing to do is to just trial and error it. So keep increasing the power of 2 until you get over the threshold that you want. And in this case, 10 toppings is what works. Okay. So, any questions there? Okay. All right. So in that case,